So how do we decide what the bound is going to be? Well, what we're doing when we're solving this eigen condition or eigen problem is we are forcing the left-hand side to equal the right-hand side. If we don't know what the solution is going to be, one way to figure out, where's the period that I'm trying to solve would be to plot both sides of the equation and look at where they intersect, because that's the solution to the problem. So here, in this example, we've taken the left-hand side, minus k over hw times lambda w, and plotted it. It's just plotted as a function of lambda w, which is what we're using to solve. So this is just a negative linear equation, right? Starting, it intersects at 0 and just goes down. On the right-hand side, we have tangent of lambda w. So if you plot that, you get these curves here, right? The tangent curve. Where those intersect is the eigenvalues, right? Or it's the eigenvalue times w. So you could do this by looking at the period of lambda, or the period of tangent, and seeing where does that usually reset. And from that, I would know, okay, my first eigenvalue is going to have to be in the range minus pi over 2 to pi over 2. The second one's going to have to be pi over 2 to 3 pi over 2, because that's where tangent resets, or that's where tangent is defined, and so on. So I always know that if I set the lower bound and upper bound, it's going to find the intersection within that window. So theoretically, though, I could also look at this and say, all right, I see that there's a minus sign in front of that left-hand side. I know my function is always going to be negative. So I know the intersection is always going to have to be between pi over 2 and pi, or 3 pi over 2 and 2 pi, as opposed to the full range. So if you wanted to help your solver out a little bit, you could say, just look in this box, right? And then repeat it and look in this box. And that's basically how you decide what the period should be. And then you have to think of how do you express that in Python in terms of the index I. So for this example, what you can do is use a root finding method. There's two that I have found to work. The first one I recommended actually didn't work fully for the problem, so I just went back and looked again. So there's one called root scalar. That was the one I recommended at first. It turns out for root scalar, if you don't provide really careful guesses, it'll always just solve for the 0 lambda value, which isn't that helpful to you. So this fn bound function provides a way of actually solving for a root within a specified bounded bracket. So here what you need to do is you start off by defining some function that gives you back the error between the left-hand side of your eigen condition and the right-hand side. So the left-hand side we said was minus k times lambda over h times w. Or h, let's say it again. Minus k times lambda over h. Okay. I'm going to give this function, though, an argument lambda times w. So it's always solving for lambda times w, because that's the thing that's going to scale from 0 to pi or 0 to 2 pi. So as long as I'm solving for that product, later on I could come back out here and divide by w. So I'm going to multiply everything by w over w, which gives me that lambda w argument. So that's where that left-hand side comes from. The right-hand side is just the tangent of lambda w. That's the same. So again, I want this function to tell me how far off I am from left-hand side to right-hand side. And I do that by taking the difference of the two and then squaring it, in this case, because the function I'm going to use is going to try to minimize that difference. It's going to try to basically force the function that you have down to 0. So by doing the square, it sort of takes away the negative sign. Otherwise, it would just force as large a negative number as it could, which isn't what you want. So then here we have our actual problem, or actual setup for the problem. We allocate space for the lambdas, or lambda w, whatever it is. You first provide your lower bound. So this is going to change with your index I. And we're going from trying to solve for the first eigenvalue all the way up, and then the upper bound is going to be the lower bound plus whatever the range is. So here it's just pi. So we're incrementing over all of this, and we solve or call this function every single time, passing to it the name of the function, right? So here this is eigenconditions, it could be whatever you want to call it. The name of the function, any additional arguments you want to provide, additional beyond lambda w. So it's always going to be passing at least one argument. Anything else you want to pass it, h, w, k, etc., would show up here. Your lower bound, your upper bound. And then what I get back from this is my lambda w, so I'm dividing this by w here. So I could do this. Hopefully it runs. Run. And it gives me back my lambda values. So I mean that's basically how you do that. And this is, you're going to have to do this for your homework, okay?